we're actually switch gears a little bit and start talking about relaxation. Um, so before I begin, I think everyone knows that project proposal updates are due by 5 p.m. today, right? If you want full points. I think most people are getting those in, so that's great. Are there any questions on that? Yes,
We
question
have to get feedback from the
from,
project too.
oh, I didn't send you feedback?
Oh no, like second feedback.
Oh, did I approve your project already?
You
Just
just resubmitted.
Did you resubmit it?
Yeah,
Did you look at the score
it was two.
still? I was like, you have updated, I think, all of them.
yeah, I think they're all 5 now. Check
Yeah.
with Katie if,
You should double check,
Okay.
yeah.
yeah, and then you can look at the comments or whatever on Gradescope. In general, I basically approve everything after one round of feedback because I'm like, either got my feedback or you didn't, and we can't iterate forever. So,
we don't get any feedback.
well, I think if there is feedback, you just look in the comments for the feedback.
Like
Have you looked at Gradescope yet?
Yeah, second feedback.
Yeah. If you want more feedback, feel free to email me. But I think I probably, in general, I said like if you revise your proposal, but like if the increment, like if you only change your proposal a little bit, I'll still approve it. I'll just say, don't forget my previous feedback. Because the feedback is given for a reason, because it's sort of meant to help you improve your project. Yeah.
Thank you.
So, because yeah, we don't have time to give endless feedback. Yeah. Okay, any other questions? Okay. So just one comment. I think everyone did very well on the pre-lecture quiz. I think there was the one where which profile would we do better for grappa for coil one or something like that. And the bottom line is, you're given, it really came down to, I think, if I had a coil profile, one was like this and one was like this, right? And so if you think about the Fourier transforms of these two, this is going to be wider, and this is going to be narrower, right? Okay. And so which one works better in general for grappa? You want the wider Fourier transform, right? So it does more blurring. So I think that was just an issue of people like once you plot it out, then it would be sort of, I think it's fairly straightforward. Okay. But if you have questions, let me know. Okay, so let's talk about, we're going to revisit relaxation, and remember we talked previously about T1 and T2, where T1 was the return to equilibrium of M sub Z, and T2 was the return to equilibrium of MXY, the transverse component. And this is what the magnetization looks like. So it sort of decays away in the transverse plane and it recovers in the longitudinal plane. And typically, as you saw in the homeworks, the T2 is much shorter than the T1. And therefore, it sort of spirals down and then grows. And we talked about how different tissues have different T1 values. And so now we want to talk a little bit about what governs T1. And then we're going to talk about what governs T2. And then we'll talk a little bit about susceptibility related relaxation. And then we'll talk about sort of how do you set up the pulse sequence parameters to take advantage of these different relaxation time constants and just to get the image contrast that you want. Okay, so the first thing is T1. So remember, T1 is sort of like, you can think of it this way, that we sort of, when we flip the magnetization down, right, we've sort of put the spins into a higher energy state, right? And the T1 relaxation is them falling back to their low energy state. But it's sort of interesting that they don't actually want to do that too quickly without some encouragement. It's sort of like, that example we talked about, in the parking garage. It's sort of like there will be a Boltzmann distribution. And so most of the people will park on the bottom and not so many on the top. But then let's say, I don't know, you put some energy into the system, you like make free hot dogs available on the top. So everyone drives up to the top, right? And they just sort of tend to linger there. And you'd think they'd all go back to the bottom, but they don't. And so if you actually waited without any additional encouragement, it sort of takes a long time for them to go back to the normal state. So what you actually need is you need some encouragement. You need to sort of, and this is what's called stimulated emission, which is basically you need something that says, oh, go back to your other energy state, okay? And what this is typically you need some sort of interaction. So you need sort of molecules that are spinning at the Larmor frequency, sort of just random spinning at the Larmor frequency, such that they can interact with this one, and so it can sort of give its energy up to this and go back to its energy state. Okay, so you need sort of these interactions to occur, and these are what are called dipole-dipole interactions. Okay, and the idea is that every proton, right, acts as its own little magnet that we talked about. Okay, and as it tumbles around, it's creating a time-varying magnetic field, right, at a certain frequency. So to help the spins relax, you need ones that are tumbling at the Larmor frequency. Okay. So this is what this is showing you, basically, that if you have molecules tumbling at the correct frequency, then there's the T1 relaxation time constant is very low. And if they're not really tumbling at the right frequency. So here there's tumbling too fast. So this is free water where they're very fast tumbling rate. In this case, where the tumbling rate is above the Larmor frequency. So there's not a good interchange. And here, for example, if the tumbling of the molecules is very slow, say in ice, where they're sort of restricted, then also the T1 relaxation rate tends to be slow. Okay, so there just needs to be sort of this interaction with other spins that allows for this relaxation to occur. So this is sort of what's known as the Goldilocks principle. Yes, question.
Intuitively, if you have more molecules spinning at the same frequency, it would kind of intuitively feel like they're spinning longer at the same frequency instead of actually going like short and faster to the relaxation state.
So the way to think about it is like, let's say I'm spinning around and I have a ball, right? And I want to pass it to one of you guys, right? It's actually easier if you're spinning at the same rate. So then we're in sync and I could just pass it to you and give up my energy to you. And if you're spinning too fast or too slow, like then when I throw the ball at you, it sort of bounces off of you.
So the person's actually getting the energy to the water.
Something, yeah. These are all like very like the true way of explaining it would take too long. So this is like, the layman's way of explaining it. Like how you'd explain it to like a 5-year-old. Which is it's sort of correct, but not quite correct. Right?
Really smart.
Yeah, really smart 5-year-old. But it doesn't take very long for a 5-year-old to ask you questions that you can't answer, right? Like, why is the sky blue? The explanation is really complicated, right? Okay. What causes rainbows? Does anyone know? Yeah, well, but I mean, huh? It's really hard. It's even to explain to a grad student is difficult. I was sitting with my son who was a graduate student. We were like saying, wow, we have no idea how rainbows occur. And we came up with all these theories. And then I went up and looked online. We're like, all wrong. Okay. Anyways, so the Goldilocks principle is, I think does anyone not know who Goldilocks is? Goldilocks and the Three Bears? Okay. You don't know who Goldilocks? Okay. So story time. So Goldilocks goes and there's these 3 bowls of oatmeal or something porridge. And one is too hot and one is too cold and one is just right. So I think she eats the one that's just right. And the bears come back and they notice something's wrong. Okay, so that's the idea. So the idea is if something's too fast or too slow, it's like too hot or too cold. And so just right is right at the most efficient relaxation rate is where the tumbling rate is close to the Larmor frequency. Okay. And so typically things that are free water tend to be too fast. Things that are in like say fat or macromolecules are tightly bound, they'll tend to be fairly slow. And sort of things in between will tend to have, at least for the frequencies we're worried about for now, basically will have the right frequency. Okay. But this also explains what happens as we change the Larmor frequency. So for example, if we're at, say, a 3 Tesla system, maybe we're in a regime where there's a lot of bound and hydrated layer water. So water that's tumbling at the right frequencies. But let's say we go from a 3 Tesla to a 7 Tesla or even a 10 Tesla. Now all of a sudden my Larmor frequency is much higher. And so I'm in a regime where there's less molecules that have that sort of tumbling rate. And so therefore, what tends to happen is the T1 tends to be very long, gets longer. Okay. T1's always very long in liquid, but if you're talking about things like gray matter or white matter, now you've sort of shifted your Larmor frequency out of the sort of the sweet spot for those spins. Okay. Oops. Okay. So for example, fats and oils. Let's see. Oh yeah, these tend to have fairly short T1s, and so these basically they sort of have the tumbling frequency is at the right rate. The other thing that we really won't get into is you can actually there are MRI contrast agents that are designed to have the right tumbling rate, and so those can also shorten the T1. Okay. So that's T1. T2 is a different mechanism, although it's related to T1. But fundamentally, it has a slightly different mechanism. And as you can sort of see here, as we talked about, the T2 values tend to be shorter, except for things like liquids. Okay. So remember, T2 is caused by thinking about to keep it simple, what's the magnetization in the transverse plane? And so when we tip all the magnetization initially, all the magnetization has the same phase. And then we're waiting for the magnetization at different places to get out of phase. So if we're in a single voxel, we're basically looking at how does the magnetization within this single voxel get out of phase. And that's due to dipole-dipole interactions. Okay, essentially, remember the rate at which a single spin rotates or precesses its Larmor frequency. That Larmor frequency depends on its local magnetic field, right? So anything that changes its local magnetic field will tend to change the Larmor frequency. Okay, so if I have another spin here, I create a magnetic field, right? And if I just like tip myself a little bit, that changes the magnetic field, which would change the magnetic field this field, so it can get out of whack. Okay, so but the effect this spin has on this spin depends on what this spin is doing. So if this spin is going like this and just like randomly moving around, what is its overall magnetic field average to? 0, right? So that's called sort of motional averaging. Okay. So if I'm in a regime where all the spins are just randomly coming around very quickly, then their net sort of influence on this is very small because the motional averaging is averaged out the net field. And so therefore what we see is when the tumbling rate is very fast, the T2 is very long. Okay. Because essentially it takes a long time for spins to get out of phase because they're all seeing a fairly uniform field. On the other hand, let's think about a mechanism where I am in a regime where the tumbling rate is very low. Okay. So this is the spin, and then this one is just like within the time regime of the experiment, maybe it's sort of almost static, right? And here's another spin, and here's another spin. And they're changing a little bit, but on average, they are changing the magnetic field that this feels, all right? And then this one is also changing this magnetic field. So they're all sort of affecting each other at the same time. And because they're sort of randomly oriented, there's sort of this random orientation of the field contributions. And so that's going to get the spins out of phase fairly quickly, right? Yes, question.
Could you please repeat what the x-axis is?
Yes, it's the tumbling rate. So fast tumbling rate is like this, and slow tumbling rate is like that.
The tumbling rate is how fast the magnetization of the...
No, it's like thermal motion. Like everything is vibrating all the time, right? So basically it's just thermal or just, yeah, basically, whatever motion is occurring. And in biology, there's also motion due to, other things, but at these frequencies, it's primarily just a thermal motion.
how fast they are moving, like.
Well, it's how fast they're moving, and it's also dependent on their environment, right? So their chemical environment. So if I'm water, the spins are very mobile, so they can sort of tumble around. Like if you look at water molecules in the liquid, they're just like that, right? But if the proton is attached to like an ice, like if I freeze the water and it becomes ice, then all of a sudden they can't really move that easily. Okay. Or like, for example, if I'm in bone or cartilage, then the spins are quite bound and that they can't really tumble as easily. Okay. Yeah. Okay. So these are some additional examples of, so what you see here is in the fast regime, both T1 and T2 are quite high, but then T1 has this sort of dip here. It's got a sweet spot, whereas T2 sort of has a little dip, but it's overall just decreasing with tumbling rate. Okay. And so you can see that here where water here has both high T1 and T2s. And then if you look at ice, it's also got a high T1, but look at its T2, it's incredibly short. Okay, so that's what you're seeing at that deviation. So basically, if you go back to here, this is water, right? And this is ice. Okay, and so that's what you're seeing, the T1 and T2 values changing. Okay, so let's just to sort of consolidate understanding, we'll do this. I'll set the poll up online and then you can just think about this for a couple of minutes. So essentially, I have a vial of liquid. The T1 is 1,000 and the T2 is 1,000, right? I add some gelatin to the mix. I mix it up and I let it to gel. I go and remeasure it. Now, what do you think the T1 and T2 values will be? Okay, so go ahead and feel free to talk to your neighbor, think about it, and we'll regroup in a couple minutes. Polls, quizzes. Okay, let's sort of take a feel for how people think. So at the count of three, just sort of say what you think the answer is. 1, 2, 3.
E.
E. Okay, so let's check that. So first of all, let's go and cross out all the things that can't be correct, right? So can A be correct? No, right? Because we've changed something about the tumbling rate. So something had to change, right? Okay. Can F be correct? Yeah, why can F not be correct? Or can it be correct? Yeah, T1 is smaller than T2, and we know that T2 is always less than T1. Okay. What else can't be correct?
Everything except B.
Let's get there. Maybe that's true, maybe that's not. So B can't be correct because the T2 can't have gone up, right? Is that right? It had to have gone down, right? Okay. And C can't be correct because T2 is greater than T1, right? Okay. So we're left with D and E. And so the question is, can we actually tell whether one is correct or not? So they're both such that T2 is less than T1. So they both could be okay. in the one case, T1 went up, and the other case, T1 went down. Okay? In both cases, T2 went down. So that makes sense. Okay. But really, we can't really know whether either of these is correct or not. Okay. Because it depends on where we are on the curve, right? If we were here on the curve and the gel took us here, right, then the T1 would go down, right? But if we were here on the curve and we went to here, then the T1 would go up. Okay. So in this case, either D or E would be a correct answer. Okay. Because essentially we don't really know where we started off on that curve of tumbling rate versus T1 relaxation constant. Yes.
But if they were equal at the beginning,
Mhm.
and T2 can never be bigger than T1,
Mm-hmm.
then T1 is at its minimum,
T1 is at its minimum.
because T1 cannot, T2 cannot be bigger than T1, right?
Okay, okay, let's just check that. So you're saying we had to be here like that?
Yeah.
Okay. Oh yeah, so you say so there, okay. So you're saying that E is correct. Okay. Yeah. You're probably I would agree with you that that's probably correct, but it depends on what this curve actually looks like. You see how we could be actually here.
Oh, they could overlap.
Yeah, yeah. So it depends on the details. So essentially, you are correct, but you know the shape of this curve can vary. Okay. Yeah. So in that case, if the curve looks like that, it's more likely the answer is D actually, right? Because then, yeah. But it also depends on how much gel you added, because you could have gone from here all the way over to here. So we don't know. So in that case, both could be correct. Yes. Yeah.
Magnetic fields, do we have a different curve while we're moving up the curve?
This curve is the same. It's just where you are. The tumbling rate. So the magnetic field only determines where you are on that curve. But the relationship. So yeah. So basically, the T1 versus the tumbling rate is sort of that's more just based on the physics. Yeah.
Same shape of curve, and the tumbling rate is going to depend on the magnetic field instead.
Yeah. So basically, okay, let me just let's see. Oh yeah, no, the relaxation, sorry, let me correct that. So the relaxation rate will depend on the tumbling rate. So basically, well, I mean, for example, if I'm at this let's see how we can put this, make sure I explain this correctly. Okay, yeah. So no, that for if I change this, the sort of the sweet spot for the T1 curve always occurs at the Larmor frequency. So as I change that, that sweet spot changes, but it just turns out that it's going to move up like this. Okay, because the relaxation times are all going to get greater because there's less spins available that have that tumbling rate. So it's sort of, yeah, I mean, the way to think about it is it's sort of hard to show on this one curve. The idea would be if I have absolute fast and slow, right? If I have F sub C like that, then there's going to be this sort of thing here, right? But then let's say I go to some other lawnmower frequency, then what you would expect to see is something more like this, right? There's going to be a shift of the whole curve, but it's also all the times are going to be longer. Okay. Yeah.
Is there any relation between T1 and T2, like is T2 less than T1?
Yes. Well, what we showed in the homework is T2 is always less than T1. And it's because some of the mechanisms that give rise to T1 also influence T2. So T2 sort of experiences both mechanisms. Yeah. That's another way of looking at it physically. And then mathematically, you show that it had to be true as well. Okay. Okay. So any questions on that? So that's sort of just a very quick overview of how to think about T1 and T2. You could write a whole PhD thesis on this, but we're only going to spend 20 minutes on it. Okay. Another thing we want to talk about is something called static inhomogeneities, because that's also a big area. And I think some of you might be looking at metal implants. So this is something that's relevant to that, which is essentially, everything up to now, we've assumed that we have this beautifully perfect magnetic field. It's uniform. And then we apply these gradients and they're perfectly linear. And the engineers try to do their best, but in real life, it's really hard to get things that uniform. And so typically what happens is when a magnet ships, it's already fairly good, but then it gets to the site and then there'll still be sort of this process of shimming where the engineer will put in like little pieces of metal or iron to sort of shim the field and get it uniform. Okay. And so the idea is that the instrument itself is uniform. And you'd think that's great, but then the other thing that happens is once you put in anything biological, that sample is now going to interact with the magnetic field and it's going to create its own inhomogeneities. So the object itself is going to take this beautifully uniform field and distort it. Okay. And so this is sort of, some of you may remember from E&M, your E&M courses in physics of like diamagnetic and para or ferromagnetic. Okay. And so these have different, what are called magnetic permeability or susceptibility. The way to think about it is things that are ferromagnetic tend to like concentrate the field. Like the magnetic field likes to go into them. So they'll sort of attract the field into them. And so you sort of see this bending of the fields into them, where diamagnetic tends to create an opposing internal field. And so it sort of repels the field around it. In either case, because there are diamagnetic and ferromagnetic materials in the body, these will tend to distort the fields. Okay. And so on the one hand, this is a problem, and we'll see why it's a problem. On the other hand, this problem is the basis of fMRI, which is a huge research field. So the history of MRI is essentially everything that's a problem is also like a new area of research. And so, and can be a brand new field. Okay. So that's sort of the cool thing about MRI, that almost anything you discover, a lot of times at first you're like, oh, this is really terrible. And then 10 years later, someone realizes, oh, this is really great. So, yeah. Okay, so here's a look at why it's not so good to have field inhomogeneities. And so what we're showing you here is, well, this is just showing what they look like. So this is sort of a map of, sort of 9 slices through a human head. And what you're showing you here is just the fact that this is the magnetic field, and darker field just means it's sort of probably lower than the surrounding field. So the color, the grayscale weighting just indicates the value of the field. And so you're sort of seeing these really sort of large inhomogeneities towards the front of the head. Okay. So anybody have an idea of what causes this, aside from Katie? Katie's not allowed to answer. So why would there be such, so in a human head, so if I put your head, if I put you in the scanner and I measure the magnetic field, there's going to be this huge inhomogeneity right around the front of your face. So what causes that? Any ideas?
Electricity.
Electricity? Yeah. So what do you have? Like what does any, so obviously you have your nose, right? What's around your, yeah, go ahead. Yeah, the sinuses. Yeah, those big air pockets, right? So you basically have these sort of, and the air pockets have different magnetic susceptibility than the surrounding tissue. And so you've sort of got this place where the composition of the magnetic susceptibility is rapidly changing. And so you've got these really quickly changing fields. And so it tends to be around here and also in your ear canals. If this picture doesn't have that, but we would also see the fields changing. You see a little sign of it here maybe, but so that's one thing, for example, that we have to deal with. So what causes that? Well, the idea is that, remember, when we excite the spins, we assume that they're all in sync. And then let's assume we have some sort of magnetic inhomogeneity where the color just represents how in the sort of the field strength. And so depending on where the spins are, they're going to, let's say the spins, are sort of in different locations, right? Then each spin sees something a little different, right? So they're going to get out of phase, right? And if I make that inhomogeneity even greater and I put the spins in that field, now they see even different spin, a greater inhomogeneity of spins. And so they get out of the phase even quicker, okay? And so if you look at the net sum, this signal with some inhomogeneity, the signal dies off at a certain rate. And the more dephasing there is, the more quickly the signal dies away, okay, just due to these static inhomogeneities. And so the way we've talked about T2 before, the way we model that is we just introduce another term, T2 prime. Okay, so here was T2, and now we just introduce something called T2 prime that takes into account this added sort of phenomenon. And so it turns out that we define this new thing called T2 star, which is defined as 1 over T2 plus 1 over T2 prime. And so the interesting thing is this T2, remember, is due to random motion of spins. So since it's random, it's not reversible, right? Because it just was random. But this is due to something static, so it should be reversible. Like if we know what caused it, we should be able to reverse it, okay? And that is, in fact, what is done with a spin echo sequence, which is something that is a bread and butter technique used all the time. There's probably lots of spin echo sequences being run right now. And so let's take a look at what that is. So T2 star decay, and we'll start getting also into like pulse sequences because we need to look at that when we talk about image contrast. So we've talked about the RF pulse, and here it's a sync pulse, which we'll talk about later, why it's a sync pulse. We've got this slice left gradient and slice refocusing pulse, which we'll talk about later. And then we've got this, which you saw in the spin warp before, right? Okay. And remember, at this point in the spin warp sequence, you're at the center of K space, Kx equals 0, right? And so typically we define something called TE equals echo time, or time of echo. And that's typically defined as where are we at the center of, where are we at Kx equals 0? Okay. And so you can sort of see here, if my object was a rect function, then I would expect to see a sync function as my Fourier transform, right? Because I'm at the center of K space, then I just have the Fourier transform at Kx equals 0. But because I have this additional T2 star weighting, then this weighting here causes such that I get sort of this weighted sync function. So its amplitude is decreased, and it's also sort of asymmetric a little bit, okay? So this is what's called a gradient echo, all right? So a gradient echo will tend to have T2 star weighting, all right? And so these are examples of what happens with the gradient echo sequence. So if I did a gradient echo sequence, what do you think is going on with this person here? Does he really have holes in his bone? Probably metal implants, right? So the metal implants are causing the fields to be very non-uniform in that area. So the signal is dephasing very quickly, okay? What about this person? Does this person really not have a mouth? What do you think is causing this? Mouth opening is one possibility. Yeah, another possibility. Braces, yeah, it's dental work. Yeah, the mouth opening would be okay. You can image someone with their mouth open and it won't really change how much air is in there. But dental work will do that, okay? Because it basically changes the magnetic field, right? So so that's why sort of when you get an MR exam, they always ask you, what sort of implants do you have? That's both for imaging quality and also for safety, because for certain things, because we're also putting RF energy into it, it can also heat up the wires or the metal, and so we have to worry about that. And it's sort of interesting. Every year we have to keep on top of things. So for maybe 5 years ago, we had to really worry about metal and tattoos. There was like a big trend of metal tattoos, and so there was this concern that that would heat up, that the metal would heat up with the radio frequency energy. And then over the last year or two, we've had to worry about like there's more metal in clotheswear like now, like active clotheswear and things like that. So now we have to like make sure people don't wear that into the scanner. Okay. And then here's an example of where the susceptibility weighting is super useful, which is where, look at this image here. See all those dark areas in the image? Those are the veins, okay? And so what do you think is caused? Why do you think the veins look so dark on this image? What do you have? What in your veins? What's obviously you have blood in your veins, okay? So what in the blood could cause dephasing? Iron, exactly. So you have a lot of iron in the hemoglobin molecules. You have a lot of iron, and that iron is exposed in the veins. And we'll get into that for fMRI a little later. But in this case, this method called susceptibility weighted imaging, which is used a lot for like brain trauma or looking at, whenever anyone has potential damage to their veins or bleeding, is based on the intrinsic contrast. So this is not iron that you put into the body. This is the iron that's already intrinsic in your veins, and that's causing the susceptibility weighted contrast. Okay, so in some cases, it's great to have that contrast, but in other cases, for example, that person with braces or the person with metal implants, then you'd like to be able to do an image without that dropout, okay? So that's where we have what's called the spin echo sequence, which is was invented in 1950 by Aaron Hahn, who was at Berkeley for many years. And so the idea is this, that this is sort of like the pancake idea or the runner's idea. So basically, if you imagine my fingers are spins, right? And they're all aligned and then they get out of phase, okay? So this spin here went faster and this spin here went slower and this spin here is sort of relative to all the other spins was sort of in the middle, okay? But you notice if some spins are faster and slower, then the sum of my fingers will be less here than it was here, okay? So the idea behind spin echo is pretty simple. It's essentially you take whoever's at the beginning and you put them to the end, and whoever's at the end put them at the beginning, and you flip them. So it's called like a pancake flip, okay? So now this spin who's fast is going to be, he's still faster, so he's going to catch up. And this spin who's slower is going to slow down, and so it'll reconverge at the end. Okay, so that's the idea behind spin echo, that we tip the spins and then we wait some amount of time. This is echo time over 2. This is the echo time. And so at this point, so this spin, let's say, was slow. This one was fast. We flip the spins with another RF pulse. So it's called a 180-degree RF pulse. And now the spin who is fast is here, and the spin that was slow is here, okay? But since that spin is still fast, it's going to catch up, and this spin that's slow is going to fall back. And at some point, if we wait the same amount of time that we waited in the beginning, then we'll refocus the spin, okay? And so this is a way of getting rid of sort of static homogeneities. It can't get rid of random effects, but it can get rid of static effects. Here's a nice movie from Brian Hargrave at Stanford showing the same thing. So they dephase, we flip them, and then they rephase. Okay, so dephase, flip, and they rephase. Okay, so this is sort of either spin echo or something called fast spin echo. It is a very standard sequence that you'll see on almost every protocol. So what does the sequence look like? It looks pretty much like what we did before, except now we apply this 180-degree pulse that sort of does the flipping for us. And so essentially what you're seeing here is the ideal. That's what you get with no weighting. And then this center of K space is weighted with e to the minus t over t2. Okay, so it's still got a t2 weighting of the center of K space. And then as we go away, oh, sorry, it's let's see, where is that? Okay. So it's got a T2 weighting here. And then on addition to that, there's going to be this additional weighting that sort of goes along like this, that mirrors this weighting. So it's that, because that just represents the fact that unless I'm right at this center point, right, where everything dephases, as I go away from it, the rephasing isn't perfect. So there's still some effect. But the center of K space, which is where sort of you get the sort of average of the image, it has the T2 weighting. Okay, so this is sort of why this is sort of an example of how well that works. So this is a gradient echo image here of a phantom, and there's some field inhomogeneities that they've just imposed for this example, and you can sort of see this leads to these dropouts here. Okay, and then simply by changing the pulse sequence to go from gradient echo to spin echo, you sort of get rid of all that. Okay, so this is why this is such a powerful technique. Okay, so to put it all together, we've got transverse and longitudinal relaxation. And we've talked about T2 decay and T2 star decay. All right, where the T2 decay is just the random motion, the T2 star decay has based on the static and the random together. And then the longitudinal is just the T1. Okay. So now we want to put it all together and talk about how can we use the fact that different tissues have different relaxation rates and how can we accentuate different contrasts. Okay. And so we're going to just talk about it in the most basic terms. We're going to look at how should we adjust the echo time and the repetition time to create different contrasts. Okay. So we're going to talk about the saturation recovery sequence. This is the most simple sequence. And so it's essentially a 90-degree pulse. We flip the spins from longitudinal transverse, and then we acquire image or acquire a line of K space. So that's our redout gradient, for example. And then we wait some amount of time, TR, before we apply another 90-degree pulse. Okay. And so let's look at the magnetization that we would get. So from here, at this point, M sub Z is equal to 0, right? Because I flipped the 90-degree pulse. So there's going to be some recovery of the magnetization from there. And then I flip it down again, and it's going to recover again. Okay. So that recovery is represented by this. 1 minus e to the minus TR over T1. Okay. And then as I acquire the data, remember, this is undergoing a T2 star relaxation, right? So now I have e to the minus TE over T2 star. Okay. And all that is weighted is by the density of protons. So in a gradient echo image, my image is related to the proton density, this T1, sort of T1 relaxation term, and a T2 star relaxation. Okay, so that's for a gradient echo sequence. For a spin echo sequence is exactly the same thing, except now I've replaced this with T2 relaxation. Okay, and the only thing that's different is I have this 180-degree pulse in there. Okay. Okay, so let's talk about, we're going to talk about 3 different types of scans, T1 weighted, T2 weighted, and proton density. So T1 weighted scan is I basically want to get rid of the e to the minus TE over T2 star term, right? I'd like to make it so I don't have to worry about the T2 star, right? So in this case, or e to the minus TE over T2, depending on whether I'm gradient echo or spin echo. So I'd like this to go away. And if I can make it go away, I can make by making it 1, right? So how do I do that? Well, I just make TE approximately 0. Okay. So the shorter I make TE, then I can get rid of that T2 or T2 star weighting. Okay. So typically there'll be a limit on how short you can make it, but in general, you just make it as short as you can if you want T1 weighting, right? So there's still going to be some proton density weighting, but it's all what you can't get rid of, but you have this primarily T1 weighting. Okay. So let's assume that we've set that up, and we'll assume that that's the case. Then the principle behind T1 weighted contrast is that if you look at this, if something has a short T1, it recovers quite quickly, and if it has a long T1, it recovers more slowly. So with the T1 weighting, things with a really long T1 should appear darker in your image, and things with really short T1 should appear brighter. Okay, so this will appear brighter, and this should appear darker. Okay, and then for the homework, you're just asked to do a very simple sort of rule of thumb, which is essentially here what we're looking at is the blue is a tissue at 800 milliseconds T1, and you can sort of see it recovers at a certain rate. And then the green is something that's at 1200 milliseconds, and you see it's recovering more slowly. And then what's shown here is the difference. Okay. So if we want to maximize the difference between the two, we sort of see the maximum is occurring approximately around 1000 milliseconds. Okay. So a good rule of thumb, if you're sort of like, if you're rushed for time, you don't have your calculator or anything, is you can just take the average of the T1s that you're seeing and then set your TR equal to the average of the T1s. Okay. So if I just average these, then that will tend to give me a pretty good estimate. Okay. And in your homework, that's sort of the rule of thumb that you want to just do. Just average the T1 values that you care about and then use that. And then you're going to compare that to what if you actually optimized it with the function that's in there. So these are some examples of T1 weighted images. And for example, we'll just focus on this one image here. You can sort of see here, this person here, really, really bright T1 signal here in the corpus callosum, which is sort of like the main highway connecting the two parts of your brain. And what they're saying is there's a lipoma of the corpus callosum. So for whatever reason, there's a lot of sort of fatty tissue in that area. And so remember, fat has a very short T1, okay? And so that's what's causing sort of that brightness in that image, okay? So that's T1 weighted scans. Now let's say we want a T2 weighted scan. So in that case, remember, we want to get this term 1 minus EXP minus TR over T1. We want this also to go to 1, right? So how do we make that go to 1? We make this go to 0. How do we make that go to 0? We want TR to go to infinity, right? But obviously, we don't want to wait till infinity because that's too long. So we just want TR as large, TR large. Okay. And so that might be for if you're really, really trying to like make a really pure T2 weighted image, there are scans where, for example, and typically the system will have a limit. It won't let you make TR greater than something. So like there might be, but you might wait quite a long time. It might be like 15 seconds. Okay. So if you really, really want to try to make a super accurate measurement, you might have to go really slowly and wait that long between TRs. Okay. And if you do that, then you get a spin echo pulse sequence. So you still have the proton density weighted and you have this T2 weighting or T2 star weighting. Okay. And so here is an example of the signal curves. If you have a T2 of 80 milliseconds, which is decaying at a certain rate, and a T2 of 120 milliseconds, which is more slowly decaying. And this is the difference again. And you sort of see the difference is optimized fairly close to the average, right? So we average these two, then I'll get that, okay? And so that's also a rule of thumb. If you have two tissues that you want to sort of maximize the contrast between for T2 weighting, then you might pick sort of the average as your first initial estimate. And then obviously you run simulations and other things to optimize that estimate. Okay, so here's an example of sort of where T2 weighting, let's look at this T2 weighted image. So first of all, you notice that the image is really bright sort of in these areas here, right? Okay. So what are those? Anyone know what those are? Yeah, CSF. So that's the cerebral spinal fluid in your ventricles. So that's one of your ventricles. So your brain has all these sort of spaces where you have cerebral spinal fluid, and that's sort of like the current thinking is that helps wash your brain out. So like you got to rinse your brain every night. So and if you don't rinse it, you can get Alzheimer's disease or something like that. It's sort of your body has set up this mechanism for sort of flushing out waste out of your brain. Okay. And in this case, you see in this subject cerebral spinal fluid, but they've also got this big cyst. So for whatever reason, there's something that's sort of pushing out the tissue and just sort of just totally filled with fluid now. Okay. So T2 is super, super useful for seeing areas where there's a lot of fluid accumulation. okay? Because the fluid, remember, has a very long T2. And then finally, there's proton density, where maybe you just want to see, what's the density of protons in the brain. And therefore, you want to get rid of both the T1 and the T2 dependence. So you just want a really short TE and very long TR compared to T1. And the result is something that's proton density weighted, or approximately. Okay. And so here's an example of doing some proton density weighted imaging in a subject that has some form of multiple sclerosis. And I think the idea here is these areas here sort of are showing increased proton density, which sort of in this case, I guess is a sign of progression of the multiple sclerosis. Okay. Okay, so let's sort of walk through this problem together, because this will be sort of essentially on your homework. You just sort of do a similar version of this. So these are actually three actual images from a person, probably a UCSD person. I don't remember exactly. I don't remember. So there's a T1 weighted image, a density weighted image, a T2 weighted image, and we're given these proton densities and the T1s and T2s, and we just want to sort of guess, like have an initial guess as to what to set the TR and T2. So let's go through this together. For the T1 weighted image, okay, what should the TR and the TE be? Okay, so ideally, what should the TE be for the T1 weighted image? As short as possible, right? So like 0, let's say it's 0 if I could get it, right? And what should the TR be? So this is what I'm trying to create, this image here. Oops. So I have three different tissues here, right? CSF, gray, and white, right? And look at the T1s, okay? So which of these two should I be thinking about averaging? Okay, so one possibility is 850 and 4000, right? Okay. That would make it so that so let's say we pick that, then the average would be around like 2500, right? And if I waited that long, probably both the gray and the white would have sort of relaxed quite a bit. Okay. And the idea is it's hard to see, but basically just so you can sort of see this, all this is white matter, and then this is sort of the stuff on the cortex is gray matter. Okay. So that's the white matter is all the sort of the wiring in your brain, and the gray matter is sort of the neurons that are actually doing most of the computations. Okay. So the idea is that we still want some gray white contrast, right? So CSF is got such a long T1 that it's going to not recover if we have a reasonable TR, like a TR that's close to that of gray and white. So in fact, what we want to do is we want to take the average of the gray and white in this case to optimize, because that's the contrast that's going to be harder to get. Okay. So that would be whatever that is. What is that? 2200 divided by 2, is that right? So 1100 milliseconds would be my initial guess. Okay, and then you could tweak it from there. Okay. What about proton density weighted? That's pretty easy, right? I want to make TR as long as possible. So we said like on most systems, maybe 15 seconds is as long as you can go. And then TE would be like 0, right? And then for the density weighted, we said we want to make TR as long as possible, right? Okay. And then TE, what should TE be? So this is the T2 weighted. So you sort of see that the CSF is going to be bright, right? It's really bright because it's got such a long T2. So what we want to do is we want to maximize the contrast between gray and white, which is sort of hard to see here, but you can sort of see here there is some sort of, this is like gray matter here, and this is white matter, okay? So once again, we want to take the average of those two. So the average of those two would be, what is it? What's 190, like 95? Maybe. Okay. So that's sort of how you can sort of do a rule of thumb, sort of generally you have to pick the two, like if there's three values, the ones that are closest together are typically what you need to optimize. Because if you optimize those, the other one's going to have its contrast no matter what, because it's so far out there. Okay, so you don't have to worry about that. Okay. And then, so this is what you're going to be given. So you just, for the homework assignment, you essentially, this is what's called a partial volume map, right? Okay. So, yeah, so for every, I think, I don't remember exactly, but I think for every voxel, right? I think, correct me if I'm wrong. Does anyone remember? They're giving the partial volume, right? For every voxel. So for every voxel, you're given some like the fraction of gray matter, the fraction of white matter, and the fraction of CSF, right? Okay. And then you're asked to sort of create a proton density weighted image, a T2 weighted image, and a T1 weighted image with either rule of thumb, or you're also given an optimal TR to pick, okay? So all you have to do is basically, your overall image, F, is going to be, whatever the gray matter was, right? That fraction times the correct equation, okay? Plus the white matter times there's sort of the T1 and T2 relaxation, T1 and T2 relaxation, plus the CSF and its T1 and T2 relaxation terms. All right. So basically the fraction, this fraction is giving you sort of the proton. I don't remember if we given the proton density. I think we do. Okay. And then there's the proton density. So the proton density of gray matter, white matter, and CSF. Okay. So essentially you just, the equations are the same, but you're just changing the TE and the TR, right? And the T and the TR is the same for all of these, right? But just each tissue has a different T1 and T2, right? So you're just playing around with that equation, okay? So really, it literally is just one line of code, okay? Okay, any questions on that? Okay, so let's talk a little bit about some additional things that are just good to know. I think some people will be doing the flash sequence. So so far what we've talked about is saturation recovery, and I'm just going to go over the flash sequence fairly quickly because it is used quite a lot, which is essentially the idea is if saturation recovery sequence, I tip the magnetization at 90 degrees, right? And so the longitudinal magnetization starts up at 0, and I have to wait for it to recover, right? And for example, for long T1 tissues, that's going to take a long time, right? So the idea is, what if instead of flipping at 90 degrees, I just flipped it like 30 degrees? Okay. So remember, essentially, it's just, we're talking about like the sine of the angle, right? So what's the sine of 30 degrees? Anyone?
Fraction of p.
Come on. Sine of 30 degrees. What? Yeah, pi over 6 is the 30s. So what is the sine of pi over 6? One half, right? Right? Okay. It's one half, right? Okay. All right. So the idea is if I tip it 90 degrees, I get the full magnetization. But if I tip it 30 degrees, I get half the magnetization here, right? Because it's a sine of 30, right? And plus, what's the cosine of 30? Square root of 3 over 2, right? Which is what, like 0.7, 0.8, let's say, right? Roughly 0.8, 0.85 or something. So I'm still left with a lot of magnetization up here. And I've got half magnetization down here. So that's a pretty good trade-off because now I don't have to wait so long to get back, right? So that's the idea behind flash is essentially, give up a little bit here, but gain a lot here, okay? The principle is something we talked about before, which is similar to, when you're flushing a toilet, right? Like some of these like new water saving toilets, they like have two buttons, right? You can get either full flush or half flush, right? So if you do a full flush, you have to wait a long time, longer for the bowl to fill up than if you do a half flush, right? You can get a reasonable flush, but you don't have to wait as long to do the next flush, right? So you can press that button more quickly, right? Okay, so that's the idea behind the flash sequence. And so it has this sort of complicated expression that depends on both flip angles, the T1s, the T2 stars out here, and then the TR and proton density. And there's a special thing about it, which is the signal is maximized at what's called the Ernst angle, which depends on TR and T1. Okay. So this is an example of that where the signal intensity here is on the y-axis, and 1/2 means, you know, 1 would be the best you could do. So half is sort of, you know, you're only getting half the signal that you want, that you could do, but look at the TR. I'm going at a TR of 500 milliseconds, even though the T1 is 1,000 milliseconds, right? To get full recovery, I'd have to wait for at least 3 or 5 TRs. I'd have to wait for like 3 to 5 seconds, right? So I'm going almost 5 times as fast and still getting half the signal. So that's the trade-off, okay? And then if I want to go even faster, 30 milliseconds, which is even a factor of 10 more, you know, now I'm only getting 1/10 of the maximum signal. But think about it this way, I'm going like literally 100 times faster. Okay. So in certain applications, like for example, if you want a really fast image, so typically when you put someone in the scanner, the very first thing you do is localize your scans. You just want to figure out where they are. So you don't want to spend a lot of time on that. So those initial scans are going to be these flash sequences where they're just going to very quickly get you a pretty good looking image so you can sort of tell where the subject is. Okay. Similarly, if you're imaging the heart or something, you probably want to use something like a flash. Okay. Or that's one option. The other thing that is used quite a lot that you should know about is inversion recovery. Okay. So this is what we've talked about before. So that's a spin echo pulse sequence. And then what I've done here is before I even do the excitation, I just invert the spins. Okay. And so what this does is it converts that T1 dependence into this. Okay. And it turns out that the intensity can be 0 when I set this inversion time, which is this distance here, according to this equation here. Okay. So this gives me a way of zeroing out tissues I don't care about. So this is an example here where, for example, if I acquire here, I would zero out fat. If I acquire here, I'd zero out white matter. And if I acquire here, I'd zero out CSF. Okay. So here's an example, like look at here, CSF is very dark here, right? Or the white matter is very dark here, sorry. And here it's very bright, okay? And here the fluid is very bright and here it's very dark, okay? So just by controlling my parameters, I can sort of zero out things I don't care about, okay? So that's also a very useful thing to do in MR. And these are some examples of using it to zero out, for example, fluid here. I'm getting rid of fluid. Here I'm getting rid of blood. So I'm doing cardiac imaging. It's called what's called black blood imaging. It's like I want to really see the vessel wall and I want to see all the swirling of the blood. So I might choose to zero out the blood signal so I can better see, say, the wall of the heart. All right. And this is actually an example of flare imaging where I've zeroed out here on the left, I've zeroed out sort of the fluid, okay? And here in this black blood imaging, I've zeroed out the blood signal. Yes, question?
Explain again how the function that crosses the x-axis really shows how is it computed?
It just follows this equation here, which we're not going to derive. Yeah.
And maybe more so conceptually, why?
Yeah, so basically the idea is the spins are here, right? And I flip them down like this, right? And at some point, this is going to recover, right? And depending on how, to go from here to here, at some point it has to cross 0. So basically, I'm looking at what point does it cross 0, and I'm timing it so I acquire my image when it crosses 0. Yeah. Okay. Okay, so and then here's another example where you can apply this sort of concept to just sort of suppress lots of things. And so in this case, by applying lots of these pulses, this was actually someone's PhD thesis, 20 some years ago. They're suppressing all the signal outside this vessel and trying to sort of just look at the vessel. Okay, so there's a lot of games you can play with MR in terms of by playing around with the relaxation rates, can you get rid of certain signals while keeping other signals? Yes, question. This is, let's see, is this an example of a T2 prep? This is actually based more on the T1s than the T2s. Yeah, so T2 prep. So right, so this is an example of what is called, all these are what are called preparation pulses. So like before you even do the imaging, you sort of play with the magnetization. So when you do the image, the magnetization is in a certain state. So this is basically because it's using the T1 recoveries, it's based on the T1s, but there is a way to do it on T2s as well, which would be more using like a spin echo sequence. Okay, yeah, okay. Okay, so in the last 14 minutes, we're going to start our discussion of functional MRI. So we're entering the part of the course where mostly we're going to talk about applications and just sort of things that, are helpful to know because they're just, you'll see them a lot, in scientific articles or in the press. So, so far until about 30 years ago, MRI was really just about anatomy, right? Just like what did things look like? And then in the early 90s, there was a sort of this discovery of a way to use MRI to study brain function. Okay. So fMRI, a typical fMRI setup is essentially, it's like an MRI setup, except that oftentimes the subject is doing something while they're in the scanner. In this case, for example, they might be looking at a checkerboard, maybe they're playing chess or checkers or something like that. And you might have a display and also some way that they can sort of give some input, like either a joystick or a trackball or something like that. Okay. So fMRI is fairly recent. So the initial finding was done in animals and then later in humans. This was in 1992 or 1993. And the fundamental finding was the first experiment was they were simply just shining light and then turning the light on, turning the light off. And then what they found was in the area of your brain back here, your visual cortex, they could sort of see the MRI signal go up with the light and then down when they turn the light off and up with the light and turn down. So this was really the first time that people non-invasively could sort of see what the brain was doing with MRI. And then what they noticed is there's an echo time dependence. So if they set the echo time to 40 milliseconds, they got a pretty nice signal. And if they set the echo time equal to 8 milliseconds, they got less of a signal, right? So based on what we just talked about, there must be some T2 or T2 star weighting to the signal, right? Because when you set the echo time less, the contrast goes away, right? Yes, question.
Signals caused by the nerves shooting and thereby moving electricity and generating magnetic fields?
We'll talk about that. Yeah, good question though. The answer is we sort of know, but we don't know completely. Okay, yeah. So fMRI, this is already 10 years ago, so it's probably updated, but it just sort of took off as a field. So right now, probably every major university, is doing fMRI. The fundamental trade-off that we make is, for a typical anatomical scan that you might get for a clinical diagnosis, maybe the resolution is 1 millimeter by 1 millimeter by 1 millimeter. In fMRI, we might back off. So typically we might go 3 by 3 by 3 millimeters or 2 by 2 by 2 millimeters. Or if we want to really go fast, maybe 4 by 4 by 4 millimeters. Okay. So the trade-off is that at least, several years ago, something like this took 6 minutes. Okay. Now with really the latest and greatest, you can maybe get that down to 1 minute. Okay. But it still takes time to get a nice looking image. Whereas here, this slice was acquired in like 60 milliseconds, right? And with the latest technologies, we can go through the whole brain in less than a second. Okay, so the idea is we can take a snapshot of the brain every second. Okay, and if you really want to go faster and you're not so greedy, you just want part of the brain, you go even faster. Okay. So the basis of it is what you just did, or are finished or about to finish in your homework. It's just echoplanar imaging. Okay, so this is the basic sequence that we do. So it's that zigzag pattern that you found. It's just more lines. Okay, so typically in your homework you did like 8 lines. Typically we'll do 64 lines or 128 lines, just more lines. Okay. And so what we do is we acquire images over time, and typically while the subject is looking at a stimulus pattern. Okay, so in this case, we may show a checkerboard for 20 seconds and then a blank screen for 60 seconds, and we just repeat that pattern. And we look to see in a certain, let's say we look at the signal from a certain area of the brain and we plot it here, and it looks like it's going up and down at the same rate as our stimulus. And then what we can do is we can correlate these two, right? Just run like a cross correlation, right? Calculate a correlation coefficient. And then we could do that for every voxel in the brain, and we end up with this correlation map here. All right. So that's sort of the most basic thing you could do with an fMRI experiment. It's just, you're just saying, I know what stimulus I applied, and I'm going to look to see what voxels responded to that, and then also how strongly did they respond. So here's an example of someone tapping their right hand, right? You can they're tapping the right hand, so their left motor cortex is lighting up because it's sort of a cross hemispheric connection, okay? And so this image is just showing you where in the brain there was activity. So let's just talk a little bit about what causes, to answer your question, what causes bold contrast, okay? So one of the clues that we got, right, is that there's this echo time dependence. Okay, so remember, so this means that there's either T2 or T2 star weighting. Okay, and so we know that this has to do something about the dephasing of the spins. Okay, so something is causing the spins to change how quickly to dephase. So for example, if this is going up, so this is sort of the light is shining in these areas here, right, during those times. So when I'm shining a light, somehow the question is there more or less dephasing if the signal is going up? Based on what we talked about. There's less dephasing, right? Because if the signal goes up, right, if there's a lot of dephasing, the signal is small. If there's less dephasing, these add up, so the signal is bigger, okay? So that's the first clue. It's like, oh, okay, there's an echo time dependence, so it's probably dephasing. Second clue is, well, it must be that when there's more function activity, there's less dephasing, right? So something's going on. Okay. So just to remind you, 1 over T2 star is equal to 1 over T2 plus T2 prime. This is the T2s due to random motion, and the T2 prime is static inhomogeneities. And we can also express this as R2 star as 1 over T2 star. Okay, so what we're going to look at in R2 star is just the rate of relaxation, like how fast do things decay. So let's look at it this way. So this is the picture we looked at before, right? And we said if there's not much magnetic homogeneity, there's less dephasing. And if there's a lot of magnetic homogeneity, there's more dephasing. Okay, so somehow when we're shining the light, we must be in this regime, right? And then no light is this regime. Okay, so something when we're shining light and the brain is sort of more active, somehow there's less magnetic homogeneity. And when I'm turning the light off, there's more magnetic homogeneity. Okay. And the bold signal change is essentially saying that I'm going to my echo time is fixed, so all I'm changing is the R2 star. So in the baseline case, that R2 star, I'm decaying more quickly. There's more dephasing. And then when there's an activation signal, the R2 star decreases. So I'm decaying much less quickly. Okay. And it turns out what we typically look at is we take the difference of these two, the delta bold, and we divide by sort of the baseline value, the bold 0 value, okay? So it's sort of looking at the fractional change in the signal is what you typically see. So it's SA minus SB over SB, and that turns out to be equal to approximately minus TE times delta R2 star. Okay, so we're seeing here, yeah, there is a dependence on echo time, okay, based on this equation here. And there's also dependence on delta R2 star. How much does my R2 star, my relaxation rate change with the functional activation? And since I'm seeing a positive change, I would expect delta R2 star should be less than 0. Okay, which means I'm going from a higher relaxation rate to a lower relaxation rate. Okay. So what does R2 star depend on? Well, similar to what we saw with susceptibility weighted imaging, it depends on deoxyhemoglobin. Okay. And just to remind you, so the hemoglobin molecule, right? It's when it's in your lungs, it's getting oxygen, right? And so those red dots are showing the oxygen attaching to the hemoglobin, and that brings the oxygen into your brain, okay? And then when it's in the brain and in the capillaries, and maybe even some of the small arterioles, that oxygen goes into the tissue, right? And so it comes off the hemoglobin molecule and it exposes these iron atoms. So these blue things are the iron atoms. So there's 4 iron atoms in every hemoglobin molecule, okay? So each of these iron atoms is like a little small magnet, right? So the idea is when they're covered by oxygen, they're sort of shielded from the environment, right? And then as the oxygen detaches, then that iron is able to perturb the local magnetic field more easily, right? So that's the basis of that. And so what it means is that in this state, for example, I've offloaded some of my oxygen, but not so much. And so there's some magnetic field homogeneities. And then in another case, I've offloaded a lot more oxygen. And so if you look at this, you sort of see all the iron atoms. And so there's more what's called, so deoxyhemoglobin is what we call the hemoglobin after it's offloaded as oxygen, okay? So this is more deoxyhemoglobin, and this is less deoxyhemoglobin. All right, and this is the case where I had the light activation, and this is the case where I had no light. Okay, so it's sort of interesting. When you're in your baseline state, you have more deoxyhemoglobin in your veins than when you're doing some activity. Okay. So this was sort of something that puzzled people initially because it's like you would think like if you were taking a first pass at designing your brain, most of us would say, well, probably when you're doing activity, you're using up more oxygen, so you'd have more deoxyhemoglobin. But we're finding from the experimental data is we're seeing that actually, no, actually when you're using your brain, you have less deoxyhemoglobin, and that's why the signal goes up. Okay. So somehow nature has set it up such that it's sort of opposite of what we might expect. And so it's because there's really a competition between 2 things, right? There's metabolism, which is going to use up oxygen, and there's delivery through cerebral blood flow. The brain's trying to supply you more oxygen. And so those are 2 competing factors. And so the blood giving you more oxygen is going to make deoxyhemoglobin go down, and the blood and your brain using up more oxygen is going to make deoxyhemoglobin go up. Okay. So it turns out if both of these things, if CBF went up and CMR2 went up at the same rate, everything would cancel out, right? There'd be no change in deoxyhemoglobin, right? So it must be that CBF is increasing more than CMRO2, or the blood flow is increasing more than the metabolism, and that's why we're getting this effect, right? Because now there's less deoxyhemoglobin. And that's actually what turned out to be the case, that somehow the brain, nature, or basically evolution made it so that everyone who had this setup survived, right? And everyone who didn't have this didn't, okay? And essentially it makes sense, right? Like if you need to use your brain to make decisions, you need to use your brain to decide whether that's a tiger or you need to run. So you better have enough oxygen to make that decision, okay? And if you don't have enough oxygen and you're just like 1 second too slow, then that genetic profile did not persist, okay? So all of us here have it such that the ratio of your oxygen, your blood flow increase to your metabolism increase is roughly at least a 2-to-1 ratio, and maybe even a 3-to-1 to 4-to-1 ratio, depending on what papers you look at, okay? So, and that's why we can do fMRI, because there is roughly at least a 2-to-1 ratio of increase in blood flow to metabolism. Right. So we're gonna edit on there. So don't forget to submit your proposals if you haven't already done so.